Hmm. Okay, so last time we talked about the notion of margin, and um, as you remember, this margin was positive for correct classifications and negative for incorrect. So if, for example, a point with label -1 was here, the distance was positive and the product was negative. So, and the formula for margin was target times a linear function, W transpose X. On the other hand, the distance um, was the dot product divided by the length of the vector W. And in previous classes, we minimized the error. We minimized the error or squared error or absolute error. And this method is called, oh, not method, the method is called the least squares, but we minimized MSE loss, mean squared error loss. Today, we will talk about a different approach for optimization. We will maximize probability, and this method is called maximum likelihood. But first, we should convert the distances into probabilities. So this will be our first step. And just um, before we move into 2D, I want to give you the intuition why we can work in 3D or in 2D and it's equivalent. Because if you look at the point in 3 dimensions and for example, this your vector x, then the uh, the this dot product was a height of this point. But if you know the slope of the plane, then from the height you can calculate the distance. So I don't know, for example, if this separating line lies goes through y equals 0, you can calculate the distance to this separating line. So that's why you can think about linear classification as in 3D, but also you can think about this linear classification in 2D. And in 3D, the dot product represents the height. In 2D, dot product is proportional to the distance to the decision boundary. And if it's positive, we classify a point as positive class. If distance is negative, we classify a point as negative class. And how to convert the distance into probability. So distance can take values from -infinity to positive infinity, while probability takes values in the range between 0 and 1. So to convert distance into range 0, 1, we will use so-called sigmoid function. You could use other functions, but if we use sigmoid function, then it's called logistic regression. So sigma. Um, and the argument should be a distance, but I will use just x for now, just to write the um, mathematical expression for this function. E power x over 1 plus e power x. And this function works from real line to the interval 0, 1. Or if I include infinities, then to the closed interval 0, 1. And the plot of this function looks as follows. So if this is the distance, or x, and this is the sigmoid, the plot SU looks as follows. So it goes from 0 to 1. And you can see that if x is infinity, then the limit will be 1. If x is negative infinity, exponent will be 0, numerator will be 0. If x is 0, what will be the value of sigmoid when x is 0? Can you substitute x? 1/2. 1/2. So it will be 1/2. And instead of classifying points based on the threshold for distance, like greater than 0 or smaller than 0, we can convert distance into probabilities and classify points based on the threshold 1/2. So if the probability is greater, we will assign +1. If the probability is smaller, we will assign -1. Or you can a little bit shift this threshold, then you will get different precision or recall. Okay, and how to use probabilities? Maximum likelihood principle or estimation. Typically it's called MLE because we want to find the estimation for our parameters, maximum likelihood estimate. So in statistics, we always assume that data are independent, because if data are dependent, we should learn the joint distribution, which is in most cases impossible. We don't know even distribution of individual points. So we assume independence. And if we assume independence of our data, x1 and so on, well, I will use, I hope I won't confuse you. I will use capital characters for random variables and lower characters for realizations, for real samples. So probability well, we actually can calculate the probability for lowercase. So let's use this okay. So assume that we have a point. So we have some points, and these points were sampled from random variable x I, and it has some target. I'm using the capital letters for random variables yi. But when we get a sample from this distribution, we will get a real point here. The real coordinates we will denote by lowercase I, and we call this realization of a random variable. And the target we will also denote by lowercase y. So it means that we assume that behind our data there is some distribution, which we don't know. And if we look at the joint distribution of our points, and we assume independence, then joint distribution will be just a product of probabilities. And without this assumption, you can't actually move forward in statistics because it's hard to come up with probability for just one point. And of course, it's almost impossible to learn joint distribution. So in our case, we will we will so you remember that distance is approximately proportional to the dot product. There is also normalization through factor division by the length of W, but up to normalization factor, it's proportional to this dot product. So for realizations of our random variable, so for real numbers features x, and I will use this sigmoid function instead of probability. So it will be a sigma of W transposed x1 times sigma of W times x2, and so on. And the distance before we convert this into probability is called logit, or logarithmic unit. So that's why this model is called logistic regression. So this is called logit. And so logit is unnormalized probability. So logit is a number between negative infinity and positive infinity, and probability converts this number into range 0, 1. And so this is our model. What we want to learn the position of this decision boundary of the line. And position is defined by the coefficients, by weights, by this W. Well, I should use extended vector 0 with tildes, actually. But if you allow me this laziness, I won't write tilde. So here I mean by W with bias term with W0 and X extended by 1, just linear function. Because if we don't assume the bias term, our line should go only through origin. But we don't want to constrain ourselves. So, and here's the maximum likelihood principle helps us to find this parameter. So what do you think? We want to maximize or minimize the joint probability? Of course, we want to find the parameter W such that the observed probability of data is maximal. So we want to maximize this function. And this is called maximum. Oh, this function is called likelihood. So that's why it's called maximum likelihood principle. We want to maximize with respect to parameters of our model. So in statistics, there are two different approaches. One is called parametric statistics, another unparametric statistics. In parametric statistics, we actually assume some model behind our data, and this model has parameters, and we want to learn to find these parameters. In unparametric statistics, we don't assume the model like in k-nearest neighbors. We just somehow estimate the distribution without assuming some parametric model. So, and for parametric statistics, we use typically this maximum likelihood principle to maximize, we will find parameters maximizing the joint probability of the observed data. So this is called likelihood. So the joint probability of observed data points, and likelihood depends on the observations and on the parameters. So this is a function of W, but also of the observations. And by X capital, typically we denote, well, in this case, random variable, but in this case, the matrix of all observations. X, in this case, I'm using for just the matrix of our observations. You remember with features in lines. If you observe different data, you will get a different function, and you will learn a different decision boundary. So now let's, yeah, and the line that you learn from this is called logistic regression. So linear regression, we learned minimizing error, mean squared error. Logistic regression, we learn maximizing likelihood or minimizing negative likelihood. So if I will use negative, then we will minimize. And in your problem 2, actually, I asked you to derive the formula for so-called cross-entropy loss, and cross-entropy loss is just negative log likelihood. Oh, let's talk about logarithm. So we will use two obvious ideas. One idea is that if we have what do you think? One function f, and take the negative function. This function will look like this, like this value will be negative. I hope you agree that maximizing the first function is exactly the same. We will find exactly the same parameter if we minimize the negative function. So this is the first idea, that we can change maximization and minimization problems. Just one question. Do you know which function is called convex and which function is called concave?
One's convex.
This one?
Oh, no, that's
Yeah, this is convex and this is concave. So just because you will hear a lot this convex optimization problem. And convex optimization problem is nice because convex function has a unique minimum. You will be able to find the minimum. Neural networks are not convex functions, and that's why it's hard to optimize them. So definition of convex function is that if you take 2 points x1 and x2, and draw a line through these points, then for every point in between, the value of the function in between f of intermediate point, and intermediate point can be written as lambda x2 plus 1 minus lambda x1. So if lambda is 0, I will get x1. If lambda is 1, I will get x2. If lambda is in between, it will be just a point between these two. So for every point in between, the value of the function should be smaller than the value on this line, and the value on this line is just lambda f at point x2 plus 1 minus lambda f of x1. You don't need to remember these formulas. It's just enough to understand the idea that if you take any point in between x1 and x2, the value of function at this point should be lower than value on this line that connects f at these points. So that's why it's called convex, and this is concave. But it was just a side comment. So the second idea, if we want to maximize or minimize, it doesn't matter, a function. If we want to maximize a function, it's the same as maximization of the logarithm of this function. Let's think a little bit about this. Why, if we maximize f, it's the same as maximization of log of f? Of course, we assume that f is non-negative and not equal 0. You can think about x and x squared. If you maximize x, you will maximize x squared or x square root of x. So if you use any increasing function, then maximization of the original function is equal to the maximization of the combination of increasing function and your function. Does make sense? So let's use these two ideas. Why do we want to use log? Because the product to take, for example, derivative from a product is a harder task than to take a derivative from the sum. But the log of the product will result in the sum of logarithms. So that's why typically we minimize or maximize not the likelihood, but log likelihood. So log likelihood, it's called. So instead of maximizing the product, so now we're going to the first problem. We will maximize the log of this. So, and I will use the notation of the product log of capital pi. Oh, maybe it's better to use just prod. Instead of just writing. Okay. So the first step is to write your likelihood or probability as the product of probabilities, and then we apply logarithm, because log of the product will be the sum of logs. Okay, I hope you remember this property of the logarithm, that the logarithm of the product is the sum of logs. Great. Now we will use the explicit formula for this sigmoid function. So as you remember, sigmoid function was exponent over 1 plus exponent. And I will divide by numerator just to simplify it. But typically we switch the order of these terms. Okay. So now let's substitute the sigmoid function in our logarithm. So instead of sigmoid function, I will use 1 plus this e. And now, if you compare this, oh, but wait a second. We actually didn't solve the first problem. I went to the second. So let's first solve the first problem. So, because this is for the second problem. So we need two more lines. So the first problem says, okay, if the probability that your target is positive, given the features, we define as sigmoid function. So we define as this expression. Now, because y is positive, y is equal to 1, we can rewrite this as using margin notation. So because y equals 1, I can just use y here. Y is 1, so it doesn't change anything. What is the probability for negative class? So the probability, and this is problem 1, to calculate the probability when y equals negative 1. And it will be just 1 minus probability of the positive class. And I ask you to just make calculations and prove that we will get exactly the same expression. So it will be 1 minus probability of the positive class. Then you find the common denominator. I hope you remember how to do that. Then ones will cancel out. And finally, so ones will cancel out. And finally, I will divide by numerator. So I will get 1 over 1 plus e to the power, positive power, w transposed xi. So do you have any questions about how I derived the formula for the probability of the negative class? So this was the formula for probability of positive class. Then I just used 1 minus this probability. Then I divided by e to the negative power. This became e to the power of positive. This became 1, and then it. And the goal is to understand that it also equals to this expression when we use margin. That's why we spent last time about talking about margin. So can you see that actually this expression equals to this expression if y is negative? So if y is negative, you will get negative y, it will be positive, so you will get e to the positive wx. It doesn't mean that the probability of positive class equals to the probability of negative class. it means that depending on the class, the formula will be exactly the same. They will be, of course, different for y positive and for y negative. But the expression, just the formula, will look exactly the same. And it will help us to write these probabilities because we will use exactly the same formula independently on the class. Okay, so are you okay with problem 1? Okay, so for problem 2, I had, so instead of using just the dot product, I had to use here margin, so y also. Because we just proved now that depending on the class, the formula will look as sigmoid of the margin, not sigmoid of the dot product. Okay, so finally, we use another property of logarithm that this power will go outside the sum. And can you see now the similarity with cross entropy loss function that you have in problem 2? So how to get this loss function that you see in problem 2? So from this expression, we will get negative and cross entropy loss is 1 over n and positive. But the difference is that loss function we minimize, and probability we maximize. So just change the sign, and without factor 1 over n, you will get the loss function. And 1 over n is just a constant, so typically we use 1 over n in loss functions. Does it make sense? Well, why it's called cross entropy? We will talk next week when we will talk about multi-class classification. But I can just tell now that we treat 1 over n as the probability distribution, which is called good name so when we don't know the distribution, we assume the distribution uniform. So actually, this will be treated as probability, and probability of one distribution times log of probability of another distribution is called a cross entropy. So that's why it's called cross entropy loss. But we will talk and derive this next week. Okay, so, and that's it. This is how you will learn a decision boundary for logistic regression. You can take the derivative, calculate the gradient, and apply gradient descent. In neural networks, we have two main loss functions, MSE and cross entropy loss. So, you know, MSE, now you know the cross entropy. So MSE is used for regression. Cross entropy loss is used for classification task. Okay, and now we will go to the notebook. In this notebook and your homework 4 will be about text classifications. So we will apply from scikit-learn, we will import logistic regression. Now you understand how it's trained. We minimize, so we have features, we have targets, and the goal is to find this decision boundary. So the goal is to minimize this function with respect to W. And under the hood, scikit-learn runs gradient descent, but with this function instead of MSE. I don't ask you to write this as as we did for homework 3, but I hope you understand that it's pretty the same. Take gradient of, but of this function and update the weights. Okay, let's have some fun with text data. Yeah, don't forget to write your name on the papers. So, ML10 notebook. So we'll work with tweets, and we will classify these tweets by sentiment. And if you want to upload the data, you can uncomment this line, and it will download the data set from Kaggle. And we need to unzip. And then you will see the data set here. Unfortunately for homework, the data set on Kaggle requires the registration, so you can't use this method to download data, or you need to create the token, but it's easier just to upload directly from this link. You can go to Kaggle and you will see the data sets and you can download the files here. Okay, let's look at the data. So we have some tweets and sentiment, positivo, and for negative it will be negativo because it's Portuguese. It's in Portuguese. We check if there are missing values. There are not, it's fine. We don't need to clean the data. Split into train test. So we have about 400,000 records. And now we will go through this pipeline. Tokenization. We'll split our strings tokens into individual words or tokens because this could be also punctuation signs, not necessarily words. Lemmatization and stemming, when we will cut, for example, endings like S, to reduce the number of words in our dictionary. Stop words, we will remove very frequent words because, for example, if you use I in every sentence, then maybe this word is not relevant for classification task, but it will reduce your dictionary. And finally, vectorizing. We will create a vector representation for our tweets. There is library NLTK, Natural Language Toolkit. And let's apply. So you can just split your phrase, but it will split by space. But for example, if you want to split like by the verb does and negation, there is punctuation. There is there are different tokenizers. So here I'm using punctuation. It will split like this. What? Oh, it doesn't work. Okay, it looks like it changed punct tab. Punct tab. Yeah, so it looks like they changed a little bit the name of the tokenizer. So yeah, if we tokenize with this punctuation tokenizer, you can see that it splitted the verb and negation separately. So there are much more tokenizers. This is the list. So for example, in your homework, I recommend to use tweet tokenizer because if we use tweet tokenizer, this is white space tokenizer, it just returns the index of the beginning and end of the word. So let's see. Yeah, let's use tweet tokenizer. Tweet tokenizer won't split emoticons, for example. And as you can imagine, emoticons are important features for sentiment of the text. Stop words. So you can import stop words for specific language, in our case, English. So this is the list of the very frequent words that we will just remove because most likely we will meet them almost in every tweet. But if we will create a dictionary of all the words, they will just increase the size of our dictionary. Stemmer will apply stemming. So for example, instead of does, it just leaves this strange word because it can be a deer, it can be a verb. But the idea of stemming is that it will remove the endings, for example, and leave just the stem of the word. And also it will reduce the number of different tokens. Like if you have go and goes, you will have only go in your dictionary. And let's try to apply this to this phrase. So you can see that for example, instead of since, it returns seen. So this is how stemming works. Now, back of words. The built-in function count vectorizer will count every will return the count of every token in your corpus in the entire data set of your texts. So in this toy example, I have three sentences. I like my cat. My cat is the most perfect cat, and is this cat or bread? So when we apply our vectorizer on these three sentences, it will return the all unique tokens. And as you can see, there is no I because by default it removes stop words. So there is no I in this list. After that, the method x will be a sparse matrix, and to see the elements of sparse matrix, we use this to array. This is how our sentences were transformed into lines. So, for example, the first was, I like my cat. Cat is the second in our dictionary. For in index 2, we have 1. Then like has position 4 in our dictionary, so there is 1 on position 4, and my is on the position 6. The other phrase, this my cat is the most perfect cat. The word cat was mentioned twice. So that's why on the position corresponding to the word cat, we have 2. And this is called count vectorizer. So we just, for the phrase, return a lone vector with counts of the tokens. If the token wasn't mentioned in our text, it will be 0. If it was mentioned, it will be just the number of times it appeared in our text. Does it make sense? So this is 2 example. Now let's apply count vectorizer to this 400,000 tweets. I will skip for now TF-IDF. If we have time, we'll go back to that. Oh, and also we can tokenize by individual words, which is called one unigram. Or we can tokenize by the pairs. So for example, my phrase was this one. He doesn't want to fix it. So if we will work with 2 grams or bgrams, it will create these tokens, but they will be word pairs. He doesn't want it, so on. Okay, and this model is called back of words because if you have different sentences but with the same words, you will get exactly the same vector. For example, it was bad rather good, or it was good rather bad, will result in the same vector because the count of words will be the same. It's a simple model, but at least we can somehow convert texts into numbers and process with our models. Okay, let's apply 1. This is range. If I indicate 1 to 1, it will count only unigrams. If I indicate 1 to 2, it will count all individual words and also all word pairs. But it will increase, of course, the size of our dictionary. So the most time-consuming part is to create the dictionary of these tokens because it should go through the entire data set and count. First, remove stop words, all this stuff, and then count. And then we have the vocabulary with counts of the tokens. And the size of our vocabulary is 355. Okay. Then, as you remember, if I want to analyze feature importance, in this case, I want to analyze word importance, I should scale my data and I can use weights of my linear model as the measure of the importance. Yeah, so I should scale. Let's uncomment. Well, actually, I can show without scaling. So we train linear regression or logistic regression, make prediction, and visualize. So for now, I trained without scaling, and you will see what the results looks like. Trying gradient descent on all this 300 something, 400. Well, in train, we have a little bit less weights, okay. And based on the coefficients, I can plot the words with highest weights. And here's the result. So this is without normalization. We have some words here, but it doesn't mean that with highest weights and with lowest weights, but it doesn't mean that these words were the most important because we didn't normalize. Let's now normalize, and you will see a different distribution. So normalize. And run and fit again. Actually, and normalized, I think, was running faster. Okay, so now if you look at the word distribution, you will see here Feliz and here Triste. That makes sense for sentiment analysis. So just again, I want to emphasize that if you want to use weights as feature importance measure, you should scale your features. So next step, if we keep punctuation, if we keep punctuation, and we know we should scale, so we scale our data. It doesn't matter if you use standard scaler or min max scaler. It doesn't matter. Um, so let's take a look at the metrics. So here the accuracy was 80%. When we keep punctuation, okay, it's still running. Yeah, the time-consuming part to create a dictionary. So it's running this count vectorizer object. I maybe have some outputs in my code. Oh, no, I have run this cell. Okay, while it's running, the result will look like this. So if we keep punctuation, you will see that the most important token was actually the parentheses. And now I can explain why we use Portuguese data, because the data sets, it's still running, for sentiment analysis, they're not annotated manually. They are annotated based on emoticons. And after that, they remove emoticons from the data and ask you to apply any model and classify. But the ground truth was uh, actually done based on these emoticons. And I have found only this data set in Portuguese, where emoticons were preserved in the data. And you can see the result that these are the most important tokens. Yeah, and you can see the accuracy now, it's almost 100%. What if we mm, keep, what if we do character level? So you can do character level tokenizer instead of word level. Um, yeah, we can use character level. In this case, the dictionary size will be very small because the number of characters is much smaller than the number of words. Hopefully it will run faster. But at least we will get these parentheses as tokens as well. Well, accuracy is high, and again, the most important tokens look like this. And finally, yeah, let me run this on not on one character, but on 3 grams. So it will be 3 characters. So I keep only 3 grams. Um, and on characters. It's yeah, it's run. Okay, okay. It's now transformed. Maybe I can just scroll down and show the result. So the most important feature will be actually the emoticon. If I would use 3 gram, oh, sorry, 2 gram, I would get perfect classification because I would have the just standard sad or happy face. And the accuracy now is 100%, which not surprisingly because the targets were based on emoticons. And finally, I want to show you what if yeah, here is an example on 2 grams, or on 1 and 2 grams. And you can see the most important token. So let's see. I should have the code here. What if we just parse our string? Let's see. I should have this code somewhere. So instead of just applying count vectorizer, logistic regression, if you just count, not count, if you just search for open or closing parentheses in your tweet and classify based on that, you will get also, I believe, 95% accuracy. So just parsing the text. I can find this now in my code. I want to talk about TF-ID of vectorizer and few words. So, bless you. So, instead of just count the entries of your words in your input text, you can take care of the frequency. So this is the frequency of the word in the document. So for example, if you repeat just the same word, me, then this will be larger. So, but it's normalized by the length of the document. So it's not absolute count, just 2 for cat. It will be 2 over 5 if the length of this sentence was 5. Inverse document frequency counts the how many times this word was mentioned in different documents. And the idea is that if this word was mentioned in all the documents, this word maybe is not important. So for example, if the word was mentioned in all documents, this fraction will be 1. And log of 1 will be 0. So when you multiply by this, you will just assign 0 value to this very frequent token. Does it make sense? So this is a little bit different idea how we create the vectors. So instead of counts, we will have counts, but normalized by this frequency length of the document and the frequency in other documents. And in your homework, I asked you to run 2 tokenizers, count vectorizer and TF-IDF vectorizer, and compare which is better. And the spoiler, the just count will work better. This TF-IDF is, it looks better and it works better, but on large corpuses of texts. Okay, that's it for today. Leave your papers on the desk. And now you're ready for homework